and mathematical modules, mathematical functions. This module provides access to the mathematical functions defined by the C standard. These functions cannot be used with complex numbers. Use the functions of the same name from the C math module if you require support for complex numbers. The distinction between functions which support complex numbers and those which don't is made since most users don't want to learn quite as much mathematics as required to understand complex numbers. Receiving an exception instead of a complex result allows earlier detection of the unexpected complex number used as a parameter so that the programmer can determine how and why it was generated in the first place. The following functions are provided by this module except when explicitly noted otherwise. All return values are floats. Number theoretic and representation functions. Math.ceilx return the ceiling of x, the smallest integer greater than or equal to x. If x is not a float, delegates to x underscore underscore ceil underscore underscore which should return an integral value. So let's use math module, and inside that create an examples 1.txt. So import math from math, import star. Let's use x is equal to 2.3, print ceil of x equal to dot format x dot ceil x, run 3, ceiling 3. Okay, and then math.com nk return the number of ways to choose k items from n items without repetition and without order. Evaluates to n factor, divide by in the parenthesis k factor into n minus k factor when k less than equal to n, and evaluates to 0 when k greater than 1. Also called the binomial coefficient because it is equivalent to the coefficient of kth term in polynomial expansion of 1 plus x raised to n. Raises type error if either of the arguments are non-integers. Raises value error if either of the arguments are negative. Math coefficient com return the number of ways to choose k items from n items without repetition and without order. Combination. So print number of ways. Number of ways to choose k is equal to these items from n is equal to these items without repetition and without order. Dot format is this. Format format 2 comma k 2 comma 2 comma comb 2 comma 3 2 comma 3. Let's run. Number of ways to choose k is equal to 2 items from n is equal to 3 items. 3 items without repetition and without pair is 0. K less than equal to n. K less than equal to n. 3 2 3 2. Run is 3. 10 5 10 n comma k is equal to 10 comma 5. N comma k. N comma k comma n comma k 252. Okay. Math dot copy sign x y. Return a float with the magnitude absolute value of x but the sign of y. Absolute value of x but sign of y on platforms that support signed zeros. Copy sign 1.0 minus 0.0 returns minus. Let's do print copy sign. Copy sign. One is 1.0. Copy sign is equal to 5.0, 6.0, 5.5. Return minus 5.5. Math.fabs return the absolute value of x. Return the absolute value of x. Print absolute value of this is this. Dot format x is fabs x, that is 2.3 absolute value. If I say minus 2.3, absolute value of minus 2 is. Then a math.factorial n return n factorial as an integer, raises value error if n is not integral or is negative. Deprecated since version 3.9. Accepting floats with integral value like 5.0 is deprecated. print factorial of x is dot format and comma factorial n. If I say k 120. Math.floor x, return the floor of x, the largest integer less than or equal to x. If x is not a float, delegates x.floor, which should return an integral value. Print floor. Okay, let's do it quickly. So, okay, math.fmod xy, return fmod xy as defined by the platform C library. Note that the Python expression x mod y may not return the same result. The intent of the C standard is that fmod xy be exactly mathematically to infinite precision equal to x minus n into y for some integer n such that the result has the same sign as x and the magnitude less than abs. Python's x mod y returns a result with the sign of y instead and may not be exactly computable for float arguments. For example, f mod minus 1e minus 100 1e 100 is minus 1e minus 100, but the result of Python's minus 1e minus 100 mod 1e 100 is 1e 100 minus 1e minus 100, which cannot be represented exactly as a float and rounds to the surprising 1e 100. For this reason, function fmod is generally preferred when working with floats, while Python's xmod y is preferred when working with integers. Math.frepx, return the mantissa and exponent of x as their pair me. M is a float and e is an integer such that x is equal to m into 2 power of e exactly. If x is 0, returns 0.00, otherwise 0.5 less than equal to abs, m less than 1. This is used to pick apart the internal representation of a float in a portable way. Math.fsum iterable, return an accurate floating point sum of values in the iterable, avoids loss of precision by tracking multiple intermediate partial sums. The algorithm's accuracy depends on IEEE 754 arithmetic guarantees and the typical case where the rounding mode is half even. On some non-Windows builds, the underlying C library uses extended precision addition and may occasionally double round an intermediate sum, causing it to be off in its least significant bit. For further discussions and two alternative approaches, see the ASP.NET Cookbook recipes for accurate floating point summation. Math.gcd, pointer integers, return the greatest common divisor of the specified integer arguments. If any of the argument is non-zero, then the returned value is the largest positive integer that is a divisor of all arguments. If all arguments are 0, then the return value is 0. GCD without arguments returns 0. New in version 3.5. Math.isClose, a comma b comma star comma rel underscore total is equal to 1e to 0 minus 09 comma abs total is equal to 0. Return true if the values a and b are close to each other and false otherwise, where whether or not two values are considered close to determined according to the given absolute and relative tolerances. Relative tolerance is the relative tolerance minus it is the maximum allowed difference. It is the maximum allowed difference between A and B and relative to the larger absolute value of A or B. For example, to set a tolerance of 5% pass relative tolerance is equal to 0.05. The default tolerance is 1e raised to minus 0.909, which assures that the two values are the same within about 9 decimal digits. Relative total must be greater than 0. ABS total is the minimum absolute tolerance useful for comparisons near 0. ABS total must be at least 0. If no errors occur, the result will be ABS A minus B less than equal to max relative tolerance into max ABS A, ABS B, ABS total. The IEEE 754 special values of NaN, INF and minus INF will be handled according to IEEE rules. Specifically, NaN is not considered close to any other value, including NaN. INF and minus INF are only considered close to themselves. Math.is finite x returns true if x is neither an infinity nor not a number, and false otherwise. Note that 0.0 is considered finite. Math.is infinity return true if x is a positive or negative infinity and false otherwise. Math.is NaN return true if x is a NaN not a number and false otherwise. Math.is QRT is QRT return the integer square root of the non-negative integer n. This is the floor of the exact square root of n, or equivalently the greatest integer as such that a square less than equal to n. For some applications, it may be more convenient to have the least integer a such that n less than equal to a square, or in other words, the ceiling of the exact square root of n. For positive n, this can be computed using a is equal to 1 plus integer square root n minus 1. Math.LCM least common multiple pointer integers return the least common multiple of the specified integer arguments. If all arguments are non-zero, then the return value is the smallest positive integer that is a multiple of all arguments. If any of the arguments is 0, then the returned value is 0. LCM without arguments returns 1. Math.LDEXPXI return x multiplied by 2 power I. This is especially the inverse function of f r x exp. Math.mod f x return the factorial, fractional and integer parts of x. Both results carry the sign of x and are floats. Math.next after x comma y step is equal to 1. Return the floating point value step after x towards y. If x is equal to y, return y unless steps is 0. Examples: math.next after x math.infinity goes up towards positive infinity. Math.next after x minus math.inf goes down towards minus infinity. Math.next after x 0.0 goes towards 0. Math.next after x math.copy sign math.infinity x goes away from 0. Math.perm n k is equal to none. Return the number of ways to choose k items from n items without repetition and with order. Evaluates to n factorial but divide by n minus 1 n minus k factorial when k less than equal to n, and evaluates to 0 when k greater than 1. If k is not specified or is none, then k defaults to n and the function returns n factorial. Raises type error if either of the arguments are not integers. Raises value error if either of the arguments are negative. Math.prod iterable into start is equal to 1. Calculate the product of all the elements in the input iterable. The default start value for the product is 1. When the iterable is empty, return the start value. This function is intended specifically for use with numeric values and may reject non-numeric types. Math.remainder xy return the IEEE 754 style remainder of x with respect to y for finite x and finite non-zero y. This is the difference x minus n into y, where n is the closest integer to the exact value of the quotient x divided by y. If x divided by y is exactly halfway between two consecutive integers, the nearest even number is used for n. The remainder r is equal to remainder x y. Thus, always satisfied abs r less than equal to 0.5 into abs y. Special cases follow IEEE 754. In particular, remainder x math.infinity is x for any finite x, and remainder x 0 and remainder math.infinity x. Raise value error for any non-nan x. If the result of the remainder operation is 0, that 0 will have the same sign as x. On platforms using IEEE 754 binary floating point, the result of this operation is always exactly representable. No rounding error is introduced. Math.sumprod pq return the sum of products of values from two iterables p and q. Raises value error if the inputs do not have the same length, roughly equivalent to sum iter2.start map operator.mul zip pq strict is equal to true. For float and mixed integer float inputs, the intermediate products and sums are computed with extended precision. Math.trunc x return x with the factorial part removed, leaving the integer part. This round towards 0. Trunc is equivalent to floor for positive x and equivalent to ceil for negative x. Negative x. If x is not a float, delegates to x.trunc, which should return an integral value. Math.ulpx return the value of the least significant bit of the float x. If x is not a number, return x. If x is negative, return ulp minus x. If x is positive infinity, return x. If x is equal to 0, return the smallest positive denormalized representable float, smaller than the minimum positive normalized float. Sys.float underscore info.mean. If x is equal to the largest positive representable float, return the value of the least significant bit of x, such that the first float smaller than x is x minus ulpx. Otherwise, x is a positive finite number. Return the value of the least significant bit of x, such that the first float bigger than x is x plus ulpx. Ulp stands for unit in the last place. See also math.nextAfter and sys.floatinfo.epsilon. Note that frex and mod f have a different call return pattern than their C equivalents. They take a single argument and return a pair of values. Rather than returning their second, return value through an output parameter. There is no such thing in Python. For the ceil, floor, and modef functions, note that all floating point numbers of sufficiently large magnitude are exact integers. Python floats typically carry no more than 53 bits of precision, the same as the platform C double type, in which case any float x with abs x greater than equal to 2 power 52 necessarily has no fractional bits. Power and logarithmic functions. Math.cbrtx return the cube root of x. Cube root of x. Math.expx return e raised to power x, where e is equal to 2.718281 is the base of natural logarithms. This is usually more accurate than math.e power x um, or power math.ex. Math.exp2x return 2 raised to the power of x. Math.expm1 return e raised to power x minus 1. Here e is the base of natural logarithms. For small floats x, the subtraction in expx minus 1 can result in a significant loss of precision. The expm1 function provides a way to compute this quantity to full precision. From math, import exp m1 exp1 e minus 5 minus 1 gives the result accurate to 11 places. expm1 1 e minus 5 result accurate to full precision. Math.log x comma base with one argument return the natural logarithm of x to base e. With two arguments return the logarithm of x to the given base, calculated as log x slash log base. Math.log 1p return the natural logarithm of 1 plus x base e. 1 plus x base e. The result is calculated in a way which is accurate for x near 0. Math.log 2x return the base to a logarithm of x. This is usually more accurate than log x2. Math.log 10x return the base 10 logarithm of x. This is usually more accurate than log x10. Math power xy return x raised to the power y. Exceptional cases follow the IEEE 754 standard as far as possible. In particular, power 1.0 x and power x 0.0 always returns 1.0 even when x is a 0 or not a number. If both x and y are finite, x is negative and y is not an integer, then power xy is undefined and raises value error. Unlike the built-in power operator, math.power converts both its argument to type float. Use power or the built-in power function for computing exact integer powers. Math.square root returns the square root of x. Trigonometric functions. Math.acos x return the arc cosine of x in radians. The result is between 0 and pi. Math.asine x return the arc sine of x in radians. The result is between minus pi by 2 and pi by 2. Math.atan x return the arc tangent of x in radians. The result is between minus pi by 2 and pi by 2. Math.atan 2 yx return atan y by x in radians. The result is between minus pi and pi. The vector in the plane from the origin to point xy makes this angle with the positive x-axis. The point of atan 2 is that the sign of both inputs are known to it. so it can compute the correct quadrant for the angle. For example, 8n1 and 8n211 are both pi by 4, but 8n2 minus 1 minus 1 is minus 3 into pi by 4. Math.cos x. Return a cosine of x radians. Math.dist pq. Return the Euclidean distance between two points p and q, each given as a sequence or iterable of coordinates. The 2 points must have the same dimension, roughly equivalent to a square root sum px minus qx power 2.0 for px qx in zip pq. Math.hypot pointer coordinates. Return the Euclidean norm sqrt sum x power 2 for x in coordinates. This is the length of the vector from the origin to the point given by the coordinates. For a two-dimensional point xy, this is equivalent to computing the hypotenuse of a right triangle using the Pythagorean theorem. Square root x square plus y square. Math.sin x. Return the sine of x radians. Math.tan x. Return the tangent of x radians. Angular conversion. Math.degrees x. Convert angle x from radians to degrees. Math.radians 0 x. Convert angle x from degrees to radians. Hyperbolic function. Hyperbolic functions are analogous of trigonometric functions that are based on hyperbolas instead of circles. Math.a cos h x. Return the inverse hyperbolic cosine of x. Math.a sin h x. Return the inverse hyperbolic sine of x. Math.a tan h. Return the inverse hyperbolic tangent of x. Math.cos h x. Return the hyperbolic cosine of x. Math.sin h x. Return the hyperbolic sine of x. Math.tan h x. Return the hyperbolic tangent of x. Special functions. Math.erf x. Return the error function at x. The erf function can be used to compute traditional statistical functions such as the cumulative standard normal distribution d phi x, cumulative distribution function for the standard normal distribution. Return 1 plus 0 1.0 plus erf x by square root of 2.0 by 2.0. Math.erfc. Return the complementary error function at x. The complementary error function is defined as 1.0 minus erf x. It is used for large values of x where a subtraction from 1 would cause a loss of significance. Math.gamma x. Return the gamma function at x. Math.l gamma x. Return the natural logarithm of the absolute value of the gamma function at x. Constants. Math.pi. The mathematical constant pi is equal to 3.141592 to available precision. Math.e. The mathematical constant E is equal to 2.718281 to available precision. Math.tau. The mathematical constant tau is equal to 6.283185 to available precision. Tau is a circle constant equal to 2 pi, the ratio of circle's circumference to its radius. To learn more about tau, check out V.I. Hart's video Pi is Still Wrong and start celebrating Tau Day by eating twice as much pi. Math.inf. A floating point positive infinity. For negative infinity, use minus math.inf equivalent to the output of float inf. Math.nan, not a number. A floating point, not a number value equivalent to the output of float nan. Due to the requirements of IEEE 754 standard, math.nan and float nan are not considered to equal to any other numeric value including themselves. To check whether a number is nan, use the isNaN function to test for nans instead of is or equal. Example, import math.nan is equal to math.nan false. float nan equal float nan false, math dot is nan, math dot nan true, math dot is nan, float nan true. C Python implementation detail. The math module consists mostly of thin wrappers around the platform C math library functions. Behavior in exceptional cases follow NXF of the C99 standard where appropriate. The current implementation will raise value error for invalid operations like sqrt minus 1.0 log 0.0 where C99 NXF recommends signaling invalid operations or divide by 0 and overflow error for results that overflow. For example, exp 1000.0 NaN will not be returned from any of the functions above unless one or more of the input arguments was NaN. In that case, most functions will return NaN. But again, following C99 NXF, there are some exceptions to this rule. For example, power float NaN 0.0 or high pod uh, float NaN float INF. Note that Python makes no effort to distinguish signaling NaN from quiet NaNs, and behavior for signaling NaNs remains unspecified. Typical behavior is to treat all NaNs as though they were quiet. See also module CMath complex number versions of many of these functions. Thank you.